Okay. So we're talking about heredity and Punnett squares today. And heredity is one part of the huge science of biology, which is the study of life. And heredity is just that little piece about how do living things reproduce and pass on traits to their offspring. So we've all noticed people that look exactly like parents or have something totally different. Where did that come from? And it is the genetic material that makes traits possible. So we all have in our cells this coding that tells us what kinds of physical traits we'll have. And we're looking at it in a very simplistic view today because there are all kinds of things that will have an impact on what you look like or what plants look like or different animals. So you may have, for instance, a gene that says that would give you the possibility, you would have the possibility of being very tall. But if you didn't have the proper nutrition, that gene may not be able to express itself fully because you need nutrition for your bones to grow and your body to be healthy. Without that, you may not grow really tall. On the other hand, you might have genes that would normally say you're just an average height person, but you also have a gene or something called Marfan syndrome, which doctors now think that Abraham Lincoln had, which was why he was so abnormally tall for the time. And that was his tendons were very loose and they didn't pull back on his bones. And so that let his just grow and grow and grow. That syndrome is still around today. And so someone who might just have genes for average height, if they also had genes for Marfan syndrome, they might grow abnormally tall. So this is just a study of what could happen, all things being equal. Let's take a look. These two words, phenotype and genotype, are two really important vocabulary words. Phenotype is what an organism looks like. So whether you have brown eyes, blue eyes, green eyes, black eyes, these are all that is coded on your genes, whether a dog has pointy ears or floppy ears, the color and the shape of flower petals and flower leaves. And then that last picture down there is a picture of something called hitchhiker's thumb. If you put your hand just like that, if your thumb goes back like that, which mine does, that is called a hitchhiker's thumb. My husband's thumb goes straight up, like he can't bend back at all like that. What does yours do, Tashiana?
Mine's kind of curved, but it's not. It's like the hitchhikers.
Yeah, I've done
It's
say, ooh, that looks creepy. But I mean, that's like, I have a hard time making my thumb go straight. So that is something that is a genetic code. So if you have brothers and sisters, parents, children around, and you ask them to hold up their thumb, you will see a variety of shapes there. But that is the phenotype. And I have a problem when I'm looking at two words that are very close like that, phenotype and genotype. Usually under I mix up which one is which. So I like to give myself little compensations for that. So I remember that phenotype, that PH is also in physical. So it's what you physically look like. So a phenotype is what you physically look like. But the genotype is your genetic makeup and exactly what your genes are coded for. So would those possibly be different? Why wouldn't your phenotype exactly reflect your genotype? Well, we talked about that a little bit. Your environment, your nutrition, when you were growing up, or if you have other genes that are influencing that particular gene, then that may be a reason why you don't look exactly like what your genotype would say. But also there's the fact that your genes are, your traits are really based on a combination of genes that you inherit from both parents. So a lot of the things that are most evident in you are things that are inherited from both of your parents. And that's how we get genetic diversity, which is really critical in times where there's a stress on a population, and whether that's a plant population or an animal population. The fact that there's genetic diversity means that individuals will respond differently to that stressor, and the ones that are successful in dealing with that stressor will pass those genes on to their children or their offspring. So if there's a drought and there's a plant, an individual plant that has some specific capability of dealing with dry weather rather than really wet weather, that plant will survive and pass on those genes. Okay, so it may be like today, people who are not really susceptible to COVID-19 are going to be the ones who survive and pass on those genes, because now we've got this brand new stressor in the environment that is impacting survival of particular individuals. So that's a very, very real example of what we're talking about.
Okay.
So here's two more vocabulary words that are really important: homozygous and heterozygous. And that ho is that prefix that means same. So homozygous means that you would have two genes exactly alike, that you inherited the same gene from both parents. Heterozygous, hetero is the prefix that means different. So that means you inherited two different genes from your parents. So to give a very simple example, if you have a gene for being tall from your parents, that would make you homozygous for height, tall height. If you have, like apparently I did, my dad was really tall, my mother was really short, probably I'm heterozygous for height. And I have both a tall gene and a short gene. And so I ended up being kind of average. That's very simple, but that is the idea of homozygous and heterozygous. So homo is the same, hetero is different, and that's telling you about your genetic makeup for one particular trait.
And if I can just jump in here,
Give me a second. I'm taking notes. Can you go back?
Yep. Hang on just a minute.
Oh.
You go back? Yep.
Sorry, those are two words that I got confused all the time when I was a science student myself. And a teacher gave me a really good way to remember that homozygous, homogeneous, because if you look at your milk always says that it's been homogenized. And that is to make the milk the same, have the same consistency. And so just whenever I see that word HOMO at the beginning of something, I think about homogenized milk and how it's all the same.
That's very interesting.
So that's it. That's all I got. That's just a cheesy way to remember that has helped me.
Thank you. I'm sorry, I'm a slow writer. I'm trying to write a little faster.
Don't worry about it. Also, remember that these being recorded, you can go back and take a look. You know, if you forget something or you missed something, these are recorded. Chris, how often are you putting these on available?
Most of them are available within a couple days. So this should be up probably by tomorrow on our YouTube page.
Okay. 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 I'm ready.
You're ready? Cool.
Yeah.
Thank you for telling me that you were taking notes. I'll slow down a little bit.
Okay. Thank you.
I go back. Whoops, I went the wrong way. Here we go. So here's a straight thumb right there. Let me get my pointer. I love my little pointer here. This is a straight. You have 2 genes for straight thumb. That means that you are homozygous, and there's your thumb. You're going to have a harder time hitchhiking than me. I probably have 2 genes for a hitchhiker's thumb because mine looks just like that. It points straight back like that. But if you had 1 for a straight thumb and 1 for a hitchhiker's thumb, that would be heterozygous. So how do we know which one would show up if you have 1 for straight thumb and 1 for hitchhiker's thumb? What would your thumb really look like? So the question is, what would be the phenotype of a person with a heterozygous genotype of hitchhiker's thumb? So if we made, well, we're actually going to show you this in a Punnett square. So it depends on which gene is dominant. The dominant gene will be a phenotype. So dominant means it shows you, it gets the say. So it's like the parent gene making the child gene say, never mind, sit down and be quiet. I'm in charge here. So dominance is determining the phenotype, what the organism will actually look like.
Okay. Determined. Okay.
So the dominant gene is expressed. That's the term we use for that, is the dominant gene expressed, meaning that's the one we see in the organism's phenotype. If people who are heterozygous for hitchhiker's thumb have straight thumbs, then straight thumb is dominant. So remember, let's go through that word term by term. People who are heterozygous, that means they have 1 gene for straight thumb and 1 gene for hitchhiker's thumb. If all those people who are heterozygous for hitchhiker's thumbs have straight thumbs, then that means the gene for straight thumb is dominant because that's the one that you see. That's the phenotype. That's the gene that's being expressed. So that results in the phenotype. Does that make sense?
Okay. Yeah, it does. It makes a lot of sense.
Okay. So if you have a straight thumb, a parent with a straight thumb, and a parent who gives you a gene for a straight thumb and a parent who gives you a gene for a hitchhiker's thumb, you're going to end up with a straight thumb because that's the dominant gene. Okay, so your genotype is heterozygous, meaning 1 of each. For your the straight thumb, you've got 1 of each, saying which kind of thumb you have. Then your phenotype is straight thumb. Okay.
Okay.
So if you are heterozygous for a trait, the trait that is not expressed is called recessive, meaning that trait is not seen. So that word recessive comes from recedes. So you think of something that is receding, it's something that's moving into the background. So it's something that you don't see. So a dominant gene is the one you see, a recessive gene is the one you don't see.
Oh, recessive is the one you don't see?
Mm-hmm.
Okay, I'm just gonna write the definition for recessive.
Mm-hmm.
One sec. I have an important phone call right now.
Go right ahead. Chris?
Oh, I missed it. Nope, I missed it. Oh well.
You need to call them back.
No, if they call back, then I'll answer. But I'm not gonna call back.
Okay. All right. So
I'm ready.
there's
Okay.
a situation called partial dominance. So that's when you have genes for two different things. So you've got heterozygous genotype. It results in an offspring that is totally different in its phenotype from either parent. So what the heck does that mean? A flower that is homozygous for red color and is crossed with a flower that is homozygous for white flower, it might result in a heterozygous striped flower. So maybe instead of getting, red plus white equals red because red is totally dominant over white, maybe
Right.
it's partially dominant, and you see where those stripes come in. So it doesn't totally express itself, and the white gets to express itself a little. So, or maybe it would be red and white is pink, you know? So you don't know exactly. That's called partial dominance. Okay? So let's take a look at Punnett squares, because this is all just kind of background for what we're trying to do here. Punnett squares are the visual representation of heredity. It's a table that helps you organize the information you have about genotypes. So genotypes are represented with letters. We represent the genotype of one parent on the left side of the table, and the genotype of the other parent is on the top of the table. And then we put the offspring genotypes in the table. So let me just show you what that looks like. And then it'll make more sense. Oops, we're not at the table yet. We have this. This is the example we're going to give you, and it's just a simple dominance, not partial dominance, just simple dominance. We have a thumb type where we're going to show that T, capital T, is the dominant gene, and it's going to represent straight thumb. Lowercase t is the recessive gene, and that will represent a hitchhiker's thumb. So in this example, we're going to have one parent homozygous for straight thumb and one parent homozygous for hitchhiker's thumb. So let's see what that looks like on our table. Here's the parent that is homozygous for straight thumb, two capital T's. So this side right here represents one parent. This is the parent with the straight thumb. This is the parent with the hitchhiker's thumb, two lowercase t's. Okay, so this parent has a gene with two t's. That gene is going to split, and one side of that is going to go to the offspring, to the child. So this parent has two capital T's, two genes for straight thumb that is going to split, and one of those is going to go to the child. So that child's genotype will look like this: capital T, lowercase t. It works like a multiplication table. Capital T times lowercase t equals capital T times lowercase t right there. So that's one offspring. Here's another one, another possibility. The offspring could get this lowercase t and this uppercase t, and it would look like the same thing. Why? Because those are the options that we have. Here's another possibility. This uppercase t and this lowercase t. Oops, and there's the other one over there. Okay. So this is very simple and straightforward. If you've got two parents that have the two exact same genes, then there's really only one option for the children. They are going to look like they're going to be heterozygous. In this case, because straight thumb is dominant, what will this child's thumb look like? Will it be straight or will it be hitchhikers? I'm really
Are
asking
you
you.
asking me?
Yeah, I really am.
Oh, okay, great. So the capital T is the straight, right?
Right, exactly.
So the capital T then would be the one that shows up. So they would have straight thumbs.
Oh, is this Chris talking?
Yeah.
Oh, I was asking Tatiana.
Oh, okay.
Yeah. Are you still there, Tatiana?
I think she dropped off.
Oh, whoa, whoa, whoa. No wonder she's not saying anything. Okay, then. So this offspring has a straight thumb. This one has a straight thumb. And this one has a straight thumb. Okay. What happens if one parent is heterozygous and the other is homozygous dominant? So here's our heterozygous, straight, a capital T and a lowercase t. So one dominant gene, one recessive gene. And this one is homozygous, and it has two dominant genes. So again, we multiply capital T times capital T and get capital T, capital T. We multiply capital T times lowercase t. There's our genotype. Capital T times capital T. Genotype. Capital T times lowercase t. There's our genotype. So one of the key results that we want to say is, what are the phenotypes? All of these offspring potentially would have straight thumbs. This does not mean, a Punnett square does not mean that every set of parents has 4 offspring and these are their phenotypes. What we're doing is saying, what are the possibilities? What could potentially show up? And if these two parents had many, many, many offspring, what would be the results? Because the more offspring they have, the more likely that it would be exactly or close to 50% would be homozygous for straight thumbs, and 50% would be heterozygous for straight thumbs. So if any two parents had only one child, these are the possibilities. It's 50% chance that they would be homozygous or straight thumbs, 50% chance that they would be heterozygous or straight thumbs. So what happens if one parent is heterozygous and the other is homozygous? Recessive. So there's our homozygous recessive. Here's our heterozygous parent. So this one looks very familiar, capital T, capital T. That one looks very different. We haven't seen this before. Lowercase t, 2 recessive genes. this one looks familiar, capital T, lowercase t, and this one is going to be two more recessive genes. Well, if there is no dominant, capital T, straight thumb gene in this offspring, what will they look like? Their phenotype will be a hitchhiker's thumb. So we look at our results here. We see that 2 of our 4 offspring would have straight thumbs and 2 would have hitchhiker's thumbs. The genotype is 2 heterozygous for straight thumb, 2 homozygous recessive for hitchhiker's thumb. So 50% of the offspring have straight thumbs and are heterozygous, that's these two, 1, 2, and 50% are homozygous recessive, these two, and they will have hitchhiker's thumb. So genotype for straight thumb, genotype for hitchhiker's thumb. What happens if both parents are heterozygous? There's one parent, capital T, lowercase t. Here's another parent, capital T, lowercase t, heterozygous. Both of these parents will have straight thumbs. That's going to be their phenotype because they have that dominant gene making them have a straight thumb. So let's see what happens. One, if they have many offspring, or then one, at least one option is that they would be homozygous and have a straight thumb. Another option would be that they would be heterozygous, straight thumb. Another option is heterozygous, straight thumb. The fourth option is homozygous, hitchhiker's thumb. So let's see what our probabilities would be there. So 75% of the offspring will have straight thumbs. These 3 out of 4 right here, 1, 2, 3, 3 out of 4, 75% will have straight thumbs. 25% of them are homozygous straight thumbs. 50%, or 2 out of those 3, 2 out of 4 total, would have heterozygous straight thumbs. 25%, or 1 out of the 4, would have hitchhiker's thumbs. So let's look at the phenotypes of that red and white flower that we were looking at before, where we had partial dominance. So the genotype of the red flower is going to be, that will be the dominant gene. And the genotype of the white flower will be this lowercase r. So let's see what happens. Maybe let's see what happens. Oh, there they are, the genotype. Here they are in the table. So we would have 1 heterozygous, 1 heterozygous, 1 heterozygous. All of them are going to be heterozygous, and with the genotype, or the gene for a red flower and a gene for a white flower. If that results in striped flowers, how many of them would be striped? 100%. All of these flowers that are offspring of these two would be striped and look like that. So here's another application. So we've been talking about hitchhiker's thumbs and whether flowers are striped or not. Those are not, those are very interesting and easy ways of looking at it. But there are some other not so simple or not much more serious ways to look at genetics and why we study genetics. There are some conditions, serious health conditions that are inherited. One of those is cystic fibrosis. And this is a condition in which your lungs produce a lot of mucus. It makes it very hard for you to breathe. And you have to have help in clearing your lungs every single day. So there are procedures, there are medications, there are procedures to deal with this, but there is not a known cure. So this is a very serious condition that parents might want to know about and think about what are the probabilities that if we both have this gene, what would be the possibility that we would pass this along to our offspring? So cystic fibrosis is a recessive gene. If the two parents are heterozygous for cystic fibrosis, what would their genotypes look like? One parent would have capital F, lowercase f, and one parent would have capital F, lowercase f. So both parents are heterozygous. They are not showing that gene for cystic fibrosis is not being expressed. So they may not even know that they have a gene or the possibility of passing on this condition unless someone else in their family has it. So what would our Punnett square look like? We would put our parents on the sides of our Punnett square, and then we would start doing the crossing of the genes. So one possibility is that they would have a child that was homozygous and does not have the condition and cannot pass the condition on to their children. They would have another possibility would be that they would have a child who did not have the condition because they've got this dominant F gene, but they do have a gene for cystic fibrosis. And if they had a child with someone else who had that gene, they could indeed pass that gene along to their child. They would have that same possibility by using this gene. If this parent passed on this dominant gene and this parent passed on this recessive gene. And the fourth possibility is that they would have a child who did have cystic fibrosis, two recessive genes for this condition. So if they had one child, the probability that child might have cystic fibrosis is 25% because 1 out of 4 possible combinations of their genes is for recessive for this condition. So look what our question is asking us. What is the probability their child will have cystic fibrosis? Cystic fibrosis, if cystic fibrosis is recessive. What is the genotype of a child with CF? The genotype is FF. Here is our lowercase f here. So 1 out of 4 possibilities means that is 25%. So alternatively, the question could have said, what is the probability that their child will not have cystic fibrosis? So if the question is, what is the probability their child will not have cystic fibrosis? That would be 75% because we have 1, 2, 3 out of 4 possible combinations. That means they would not have cystic fibrosis. if it said, what is the probability that their child will inherit the gene for cystic fibrosis that they could pass on, that would be without having the disease themselves, that would be 50%, because there are 2 cases here where the child will not have cystic fibrosis because they've got that dominant F gene, but they do carry the recessive gene for cystic fibrosis. So 50% of their offspring, or any particular offspring, would have a 50% chance of having that gene that they could pass on to their own offspring. So unless the parent has a child with another parent who carries the gene, whether or not it's being expressed, then this is not possible unless they are having a child with someone who also is carrying that gene. So that's a very real condition that we can see that matters a lot. And this is one of the careers that's available to people. It's called genetics counselor. And part of the job of a genetics counselor is to help you determine what kind of genes you might have that you would be passing on to your children. And this helps parents decide what they might want to do, whether they might want to have children or not. So this is, or it may help you decide what kind of medications you want to take, or how you want to treat a potential disease that you have. So these are some real life examples of why genetics is so important.
I was just going to jump in and say another example or two.
Okay.
Sickle cell anemia is another disease that's passed on like this. And then what's often called brittle bone disease, osteogenesis imperfecta. And it has a dental equivalent, dentiogenesis imperfecta, which I actually have, which is brittle teeth disease.
And is it straightforward, like dominant recessive?
It's like the flowers where you can have the striped variation. You can have different degrees of it.
Right. So, and I wonder if there's also some environmental impacts too. I mean, is there any way to mitigate the disease? Like, can you, for like brittle bones, can you increase your vitamin D? Can you increase your calcium?
It depends on how severe a version of it you have.
Yeah.
So some versions are more treatable than others in that regard.
Right. So that's another decision that another way that genetics counselors can help you is just determining the severity and what it is that you can do to mitigate a situation.